Welcome to Part 2 of the normal sampling series on incremental sampling for radioactive wastes. In Part 1, we saw that the Savannah River Site had almost 50 radioactive waste tanks to close when we proposed ISM. Each tank is a unique challenge, even with a massive infrastructure and advanced technological support. And, as we saw, the tanks are very messy. Part 2 presents two main topics. The first is the robotic approach to tank sampling. Robotics are essential to collecting the needed sample material, and we'll see 3 generations of SRS-modified commercial robots. Then we'll examine data quality objectives. The EPA's 7-step process is just as viable and important here as it is in mining, environmental, and other fields. Today we'll see how SRS DQOs accommodate nuclear waste challenges. So let's get into it. The alternative to the core sampling option shown in Part 1 of this series is robotic sampling. This slide shows TIZZY, one of the SRS robotic designs, in a pre-deployment testing facility. The robot design must incorporate capabilities that enable it to climb over the floor pipes, navigate around vertical cooling coils, traverse and potentially sample mound material, as well as being able to adapt to other unique tank features. The tank environment also contains chemical and radiological challenges that impact the robot's abilities and lifespans. This slide shows the G.I. Joe robot in action in the same facility as TIZZY. G.I. Joe has features TIZZY did not have, including a camera mount and a more sophisticated sample collection arm. This demonstration exercise also shows the issues with exceptional success in residual removal. The scrape sampler has difficulty collecting sufficient material from the remaining residuals on the tank bottom. However, as mentioned previously, this is probably a good problem to have, as source terms close to zero are desirable. We now see G.I. Joe has the vacuum sampler device attached instead of a scrape sampler. The robot can use the vacuum attachment to collect sample material from the tank bottom. Note that both the vacuum and scrape sampler can only sample the top surface of a mound, whereas the core sampler can obtain a vertical profile of potentially segregated materials. This slide shows Frankie, an early design in the SRS robotics program. Frankie is actually sampling the residual material in Tank 19 during the pre-closure activities. Because of the harsh conditions inside the tank, Frankie didn't last long and was replaced by Frankie Jr. I highly recommend you visit the link below that shows Frankie in action, which is also posted on the Normal Sampling YouTube channel for this video. Just as the ISM program faced sampling constraints, it also faced analytical constraints. The Savannah River National Laboratory on-site needed a 70-gram sample mass to meet quality goals, known as MDCs, or minimum detectable concentrations. At this point in time, we had not identified a crucial differentiator between ISM and discrete sampling. The breakthrough moment arrived with the pairing of 2 critical needs and constraints, the first being the 70-gram sample mass, the second being the minimum mass available from historical robotic scrape samples, which at times only recovered 15 grams of material. We realized that with a typical tank sampling design of 15 locations and a virtually assured sample mass of 15 grams, we could create with a high certainty 3 ISM samples composed of 5 15-gram increments from the 15 sample locations. A 15-gram mass presents an analytical problem for discrete, standalone sampling due to the insufficient mass. With ISM, however, a 15-gram increment is sufficient at a single location because when combined with other increments, it provides sufficient mass to create the 70-gram sample needed to meet the MDCs. This pairing opened an important door, as it could virtually eliminate an ongoing problem with collecting sufficient sample mass at a single location. SRNL had other key analytical parameters to address. First, the 70-gram sample mass needed was not the only hurdle in the ISM implementation gauntlet. Historically, SRNL handled 8 to 15 discrete samples per tank. Thus, our ISM proposal of 3 samples would not overwhelm their capacity, nor would it create a critical work shortage. Second, the ISM option provided DOE with a financial incentive. The SRNL sample analysis cost was $1 million to $1.5 million per sample in 2010. ISM offered a potential savings of millions of dollars per tank, multiplied by the 49 remaining tanks. Next, the lab analysis still required about a year, although SRNL anticipated streamlining certain portions of their workflow by implementing the ISM process. Also, with an analyte suite of 50 to 100 radionuclides per sample, ISM did not impact this process. Finally, this approach achieved reduced dose to workers, at least from dose originating at the tank farm facilities. Once we had the tank farm and laboratory on board, the next step was to start the ISM plan development. This is the perfect time to remind ourselves of the 3 ISM priorities: support, support, and support. That is, field sample support, laboratory subsample support, and decision unit support. The concept of support is not intuitive. When I tell people the mass of the sample or subsample determines the shape of the data distribution, most people are skeptical at best. When I tell them the sampling error is easily 20 times larger than the analytical error, they are very surprised, but EPA and mining applications have documented this relationship. This skepticism is why I developed experiential training, which allows the skeptics to convince themselves. This slide enables us to discuss the basic concepts that underlie why support matters and comes courtesy of EPA and Dina Crumbling. It features many of the sampling theory and practice elements I wrote about in my book on environmental sampling. So let's examine the diagram in depth. The basic idea is to compare the histograms created with the data representing different sample supports. This allows us to see the influence of the sample mass and the risks of small sample supports, which produce frequently both false positive and false negative sample results. The diagram plots americium-241 concentrations along the x-axis and the density function or frequency of observation on the y-axis. The action level of concern is 3 nanocuries per gram and is represented by the blue vertical arrow pointing downward. The true but unknown mean is shown as a vertical line at 1.92 nanocuries per gram, and we see 3 histograms representing sample supports of 1, 10, and 100 grams. We'll start the analysis with the smallest sample support and work up to the larger supports. The 1 gram sample support histogram and samples appear in green. The histogram is skewed, with a long tail to the right that goes beyond the action level. We also see sample concentrations reported as high as 7 nanocuries per gram. This is more than twice the action level and more than 3.5 times the true mean. The median, or most frequently observed value, occurs close to the graph origin and to the left of the mean. The diagram also shows 2 1-gram samples. The sample on the left shows few, if any, hits of americium, which is consistent with a histogram of mostly low concentrations. On the right side, the sample contains americium particles, perhaps a random cluster. The large number of sample concentrations near the median, all of which are below the action level and the true mean, gives us a false sense of security that the material is below the action level because most of the samples we collect result in low concentrations. The sample on the right shows the risk in small sample supports. A disturbingly larger proportion of the 1-gram samples contain americium-241 concentrations greater than the action level of 3 nanocuries per gram. These samples result in false positives that typically initiate additional and wasteful expenditures of time and money, perhaps 10 to 15% of the time in this situation. This is the first example of how the probability of a sample exceeding the action level is a function of the sample support. Note also that if the high concentration 1-gram sample is analyzed a second time, the result is likely to be a low concentration with the finger pointed toward the laboratory as the cause. This diagram shows that even if the original sample contained contamination, subsampling is likely to miss it, resulting in false negatives. In fact, the diagram shows that more than half the samples and subsamples fail to contain contaminant particles. The histogram of 10-gram samples mitigates the risks. The sample distribution is much more symmetric, closer to the true mean, and the risk of a sample above the action level is reduced, with the upper tail barely exceeding the action level. The histogram of 100-gram samples shows how larger supports mitigate this risk further. The histogram centers on the true mean value, and the histogram is narrow with low variability. This yields a high confidence of a correct classification decision and a low risk of false negatives that could have adverse impacts on human health and the environment. In a larger context, this diagram and ISM confirm the total quality management work of Dr. W. Edwards Deming, who determined you cannot inspect quality in, you must design it in. If we don't design samples properly, we risk spurious sample results. Recognize also that more vigorous laboratory inspection and oversight will not solve the problem. If you missed the contaminant material in the original sampling, you won't find it in the lab. And if by chance you did sample a cluster, a resample will not necessarily replicate the high original result. The moral of the story is to use ISM and appropriate sample supports to the maximum extent possible when trying to determine the average concentration in a decision unit. The short story on the relationship between sample support and data distribution shape is what I call the Smins Principle. Sufficient mass yields normal samples. This phrase is shorthand for a larger sentence. The mass of a sample determines the shape of a data distribution. Stephen Covey, author of The 7 Habits of Highly Effective People, exhorts people to begin with the end in mind. This same principle applies to ISM. Think about the type of data distribution you want before you take the samples. Ask yourself, do you want a skewed, asymmetric distribution such as the one on the left, with the median far below the mean? Or would you prefer a symmetric, normal distribution such as the one on the right? I'll leave the choice up to you. Before we perform the fundamental error analysis, we need to develop the project DQOs. These address, among other items, the tolerable error limits. We'll start at step 1, which is state the problem. Examining the problem statement, we see a broad perspective set forth. We proposed originally a more focused statement, but ongoing efforts have proved this to be acceptable language. The principal study question underwent similar changes, with both statements addressing whether the ISM data obtained are valid to support the residuals inventory and tank closure. Step 2 focuses on defining the study goals and decisions. 3 decisions must be made. The first decision is to determine whether the waste is greater than Class C. This is a determination with more than one input. It is not as easy as calculating an upper confidence limit on the mean and comparing it to a regulatory threshold to see if it's above or below. Decisions 2 and 3 are related to the removal of radioactive material from the tanks. Decision 2 addresses the HRRs, the highly radioactive radionuclides. Here the standard is the maximum extent practical, which brings us again into the realm of subtle legal language. Decision 3 focuses on the percentage of the volume of residual material removed from the tank during the pumping process, without special regard to which specific radionuclides exit the tank. The standard here is the extent technically practicable, a higher standard than for HRRs. If this standard is achieved, it is a good indication that the Decision 2 standard will also be met. As a side note, the study goal is not to acquire one of the grout paperweights shown in the picture, although they were part of a tank closure celebration we'll see in Part 3. Step 3 focuses on decision inputs. Because tank assessment is so complicated, the decision requires multiple inputs. Input number 1 addresses the radionuclide concentrations. These come directly from the ISM sample analyzed by SRNL. Input number 2 examines the chemical constituent concentrations for chemical wastes of concern. These data also come from the ISM sample. Input number 3 are the sample densities. Historical sampling observed varying densities for the residual material, and SRNL determines the density of each ISM sample, which is applied by SRNL during the construction of the final ISM samples. Finally, input number 4 addresses the residuals volume data. These come from steps 1 and 4 in the flowchart seen in Part 1 and are used to determine the error bounds on the volumetric estimate. Step 4 is the decision unit, which is uncharacteristically simple. The boundaries for decisions are the waste tank footprints as we saw in the performance assessment for the F area tank farm. For completeness, the diagram below presents the tank locations for the H area tank farm. H area contains a few more tanks than F area, but the performance assessment and special analysis assigned radionuclide concentrations in both tank areas to the center of the tank. Step 5 addresses the analytic approach and decision rule. The DQO diagram shows two possible paths for decision making. The path on the left, which does not apply here, is essentially a hypothesis test, where we compare an upper confidence limit to a regulatory threshold. Alternatively, we will take the path on the right, which is highlighted in yellow. This path enables the stakeholders to examine performance criteria, which fits hand in glove with the site performance assessment and special analyses. Similar to problem statements, the two decision rules are less than precise but have proved workable. They both allude to situations where data exhibit potentially undesirable aspects, where alternative actions and consultations among stakeholders are required. Discussions with regulatory agencies determine the final decisions on data usability. Step 6 develops the project's decision error limits. SRS identified two prime error drivers. The first is the inaccuracies in the volume determination. The volumetric assessment looks for areas of heterogeneity, seeking color variations that could indicate different types and/or concentrations of radionuclides in the residual material. They also watch for areas where particle sizes differ. Both of these items are valuable to the ISM process and assist in selecting appropriate residual material from the tank. Ultimately, SRS incorporates the volumetric error into the overall data quality assessment. The second driver is whether they have achieved representative sampling and analysis, with the term representative always being uncomfortably qualitative. Sample support contributes a quantitative aspect to the decision. A 70-gram sample provides sufficient mass to achieve the laboratory MDCs. Moisture in the residual material can cause clumping during the drying process at SRNL, so they employ post-drying particle size reduction to maintain in-tank particle sizes. Finally, a fundamental error analysis confirms a 70-gram sample of typical in-tank particle sizes yields a tolerable error of less than 5%. Typical project goals require a fundamental error of less than 15%, as recommended by Pierre G. and Francis Bittard. The fundamental error is an insidious error for a number of reasons. First, it occurs at every sampling and subsampling stage. Next, errors accumulate and do not cancel each other out. And finally, it never goes away. For these reasons, we emphasize to SRS the importance of the fundamental error management, the acquisition of appropriate sample support, and an aggressive goal of 5% error at every sampling and subsampling stage. The final step in the DQO process is the data acquisition plan, also known as optimizing the design. At SRS, this contains three key components. The first is random stratified sampling, which will help eliminate bias if conditions allow its implementation. It may need to be combined with judgmental sampling based on volumetrics, the number of mounds and their locations, and practical sampling constraints. A tank will contain a minimum of 3 sample arrays for each tank, with each sample array containing 5 increments. This design rearranges the previous sampling plan where SRS collected approximately 15 discrete samples in each tank. Knowing that at least 15 grams of material results from each sample location, we can develop with confidence an ISM sampling plan for 3 samples with 5 increments totaling 70 grams. The second component is creating the sample using volumetric proportioning. SRNL applies the appropriate mass of material for each increment based on the volumetric assessment seen in the Part 1 flowchart to create the ISM samples. Finally, practical constraints can influence the locations for sample collection. Only 7 riser port locations exist through which sampling equipment can be placed in the tank. We can see in the bottom cartoon of Tank 20 the 7 riser ports and note their small diameters, which limit equipment size. As we saw in previous slides, in-tank obstructions exist that deny access or require workarounds to allow acquisition of the desired sample material. And of course, we must limit radiological exposure to workers to achieve ALARA goals. This wraps up the DQO portion of the Part 2 presentation. Let's start examining the ISM design details in Part 3, beginning with an analysis of the fundamental error impacts. Thanks for watching Part 2 of the normal sampling series on incremental sampling for radioactive wastes. Be sure to watch Part 1, which covers high-level waste tanks, and Part 3, where we explain the ISM sampling design. See you next time on Normal Sampling.